Welcome to this explainer. I am absolutely thrilled to have you here today because we are looking at something huge, a literal monumental shift in technology. We are talking about how the year 2026 is rapidly shaping up to be the ultimate tipping point for electric vehicles and the global power grid. For years, we've heard these lofty promises about the future of EVs, but today, we aren't looking at science fiction. We are looking at cold, hard commercial realities that are hitting the market right now. Okay, let's dive into this. We are going to literally build the solution from the microscopic chemical level all the way out to macro fleet logistics. Our roadmap today covers the EV infrastructure crisis, sodium ion's big breakthrough, the solid-state leap, how modular chargers fix everything, keeping fleets moving, and finally, the 2026 tipping point. Section 1. The EV infrastructure crisis. But before we get to the incredible new tech arriving in 2026, let's be totally honest about where we are right now. We have to acknowledge the very real friction points of current EV ownership. Because, well, to appreciate the cure, you really have to understand the disease. And this number, it perfectly encapsulates that disease. According to JD Power, 1 out of every 5 public charging sessions fails. 1 in 5. I mean, imagine if you went to a gas station and every 5th pump was just completely broken. It's incredibly frustrating, and it's a massive barrier for everyday consumers who just want to get from point A to point B without a headache.
And that failure rate is really just one piece of a much larger puzzle. It's a whole ecosystem of interrelated issues making consumers and fleet managers hesitate. We're dealing with range anxiety, especially in freezing weather where current lithium-ion batteries just lose a huge chunk of their capacity. Then there are the safety concerns regarding flammable liquid electrolytes. Plus, we've got those giant monolithic all-in-one charging stations that fail completely if literally just one internal part breaks. And for businesses, this all leads to fleet operations losing precious hours to unexpected downtime. It is a chain reaction of friction.
Section 2. Sodium ion's big breakthrough. So how do we actually fix it? Well, we start inside the battery itself. Industry insiders are calling this a potential deep-seek moment, a massive cost-slashing, efficiency-boosting disruption, kind of similar to the recent breakthroughs we've seen in AI. So what exactly happened? CATL, the world's largest battery maker, just signed a historic 60 gigawatt-hour deal with Hyperstrong for sodium-ion batteries. To put that into perspective, 60 gigawatt-hours is roughly equivalent to half of the total energy storage battery volume CATL shipped in all of 2025. This isn't a tiny pilot program. This is gigawatt-scale mainstream commercialization. So why is sodium ion such a game changer? First off, sodium is about 1,000 times more abundant than lithium, making it ridiculously cheap. But the really mind-blowing part is the performance. These cells can operate in extreme temperatures, from negative 40 degrees all the way up to 70 degrees Celsius. They completely eliminate winter range degradation. Let that sink in. An EV will deliver its full electric range even in sub-zero conditions, and they boast a cycle life of over 15,000 cycles. That's essentially 40 years of daily charging without ever needing a replacement. No way, right? But it's true. But here is the absolute genius of CATL's rollout. They designed these sodium-ion cells using the exact same prismatic form factor as their existing lithium-ion products. Zero retooling required. That means manufacturers can just seamlessly integrate these new, cheaper, cold weather-proof batteries right into their existing assembly lines. They don't lose months to adaptation costs. It's an immediate plug-and-play revolution for the grid and for cost-sensitive EVs. Section 3. The solid-state leap. Now, what's really interesting is that while sodium-ion is conquering the affordable EV market, there's another leap happening, the holy grail for premium passenger vehicles, solid-state technology. Notice the stark, undeniable contrast between these two technologies. Traditional lithium-ion batteries rely on a liquid electrolyte, and under stress, that liquid can actually ignite at around 90 degrees Celsius. Solid-state batteries replace that liquid with a non-flammable solid material that pushes the threshold for thermal events all the way up to 247 degrees Celsius. It's incredibly safe, and because they use lithium metal anodes, the energy density skyrockets from a max of 300 watt-hours per kilogram up to 400 or even 500. We're talking about passenger cars that could travel 1,000 to 1,200 kilometers on a single charge. And I want to stress, this isn't just a lab experiment anymore. We are already in phase 1 right now, with semi-solid batteries popping up in some vehicles. But 2026, that is the true launchpad. We are entering phase 2, which is the initial commercial production for premium vehicles. China is even slated to release its first official solid-state battery standard by July 2026. That lays the exact regulatory groundwork we need for Phase 3, mass global adoption by the end of the decade.
Section 4. Modular chargers fix everything.
Okay, so we've completely revolutionized the battery inside the car, but what about that awful 1 in 5 failure rate at the charging station? Well, it's time to fix the physical infrastructure, and this brilliantly illustrates the solution. Historically, chargers were monolithic. If one internal power converter failed, the entire machine was just a useless brick for weeks while you waited for a specialized tech. The 2026 solution is modular architecture. Instead of one massive converter, the system is broken down into independent, hot-swappable 25 to 50 kilowatt server rack-style modules. Let's walk through a real-world scenario to see why this is so powerful. Imagine a 150 kilowatt charger made of 6 25 kilowatt modules. Step 1. A module fails. In the old days, that was game over. But here, in Step 2, the remaining 5 modules just keep communicating and running. Step 3, the charger stays online, delivering 125 kilowatts, so it maintains 83% of its total capacity. Honestly, the driver plugging in probably won't even notice a difference. Finally, in Step 4, a technician arrives and hot swaps the broken module in under 30 minutes using standard tools. The repair time drops from weeks down to literal minutes. It's fantastic.
Section 5. Keeping fleets moving.
Now, fixing public chargers is great for you and me on a weekend road trip, sure, but at the macro operational level, reliability isn't just a convenience, it is commercial survival. When a commercial EV fleet charger goes down, the stakes are just incredibly high. The data shows that a single commercial van stuck in the depot uncharged costs a business an average of 800 British pounds, or roughly $1,000 every single day. That's lost revenue, missed deliveries, and worst of all, damaged customer trust. Fleet operators literally cannot afford to have perfectly good vehicles sitting idle just because of a frozen charger screen. And this economic reality is forcing a total redefinition of service level agreements, or SLAs. I mean, a standard guarantee of 97% charger uptime sounds pretty great, right? Actually, scratch that. If you do the math, 97% uptime means a charger can be broken for 11 full days a year. For a delivery fleet, that is completely unacceptable. So fleet managers are now demanding AI-driven predictive diagnostics. These are smart charging software systems that proactively monitor for anomalies, like a sudden temperature spike or a repeated connector error, and then alert a 24/7 rapid response team to fix the charger before the driver even wakes up for their morning route. And, when all else fails, 2026 is seeing the rise of the ultimate safety net, mobile and wireless backups. Companies are literally deploying on-demand mobile charging vans equipped with rapid chargers. Some are even using solar-powered tech to directly rescue stranded fleet vehicles. It is just a brilliant, flexible layer of redundancy that ensures no matter what happens to the grid or the station, the fleet keeps moving. Section 6, the 2026 tipping point. So we've covered a lot of ground today, from the atomic structure of new batteries all the way out to the macroeconomics of fleet logistics. But bringing all these incredible elements together, the crucial point is this. The entire EV ecosystem is leveling up simultaneously. It's not just one isolated breakthrough. It is a synchronized shift. In chemistry, we're moving away from easily degraded, flammable lithium-ion to ultra-safe solid-state and cold weatherproof sodium-ion. In hardware, we've abandoned those brittle monolithic chargers for resilient modular hot swaps. And in operations, businesses are moving from reactive, costly repairs to AI predictive maintenance. These parallel breakthroughs perfectly target and eliminate every single friction point we talked about at the beginning of this explainer. Which leaves us with this final thought. With sodium batteries slashing costs, solid-state pushing ranges past 1,000 kilometers, and modular AI-monitored chargers virtually eliminating downtime, if range anxiety is truly dead and chargers never fail, what is stopping the world from going 100% electric? The technology is here, the commercial deals are already signed, and 2026 is the year it all hits the road. Thank you so much for joining me for this explainer. I hope this helped you grasp just how fast the future is arriving. Keep learning, and I'll catch you next time.